Have you ever stopped to think about the incredible complexity hidden inside the devices we rely on every single day? Your smartphone, that smart thermostat, the massive data centers powering the cloud, they're all humming with billions of operations per second.
Uh-huh. It's truly staggering.
But how does all that data actually move around inside those tiny chips?
Yeah,
It's like this massive, invisible digital plumbing system.
that's a great way to put it.
Today, we're taking a deep dive into the AXI protocol family Advanced Extensible Interface. And as you'll quickly learn, it's not just one thing, but a whole family of standards.
Right.
Our mission today is to give you a clear, comprehensive, yet easily digestible understanding of AXI, its core concepts, its distinct variants, and why it's absolutely crucial to how your favorite devices work.
And the story of this crucial digital plumbing, well, it actually begins with ARM Holdings. They developed AXI as a fundamental part of their Advanced Microcontroller Bus Architecture, or AMBA specification.
Yeah, right.
It's truly foundational to modern system-on-chip, or SoC design. Think of it as the common language that allows different intellectual property, or IP, blocks like a processor, a memory controller, maybe a graphics unit to communicate efficiently, all within a single chip.
Okay.
And a major reason for its widespread adoption, from mobile devices to servers, is its royalty-free nature.
That's huge.
It is. That removes a huge barrier for designers, encourages broad use, and really fosters an ecosystem of compatible components.
So how did ARM engineer this digital plumbing system to be so versatile and powerful? What are the fundamental principles that make AXI the backbone of so many devices?
Well, at its core, AXI was designed with several clear objectives in mind. High performance, definitely scalability, flexibility, and crucially, low power consumption.
All key things for modern devices.
Exactly. These aren't just buzzwords. They make it suitable for incredibly demanding applications, from the phone in your pocket to massive data center servers. But beyond just raw speed, AXI radically simplifies complex SoC design.
How so?
By providing a standardized interface, it drastically reduces the need for custom, one-off communication interfaces between blocks.
Right, less reinventing the wheel.
Precisely. This minimizes overall design complexity, which in turn improves performance and reduces the risk of components becoming obsolete too quickly. Without a standardized protocol like AXI, integrating all these diverse IP blocks would lead to an exponential increase in design and verification effort, basically making large-scale SoC development impractical.
Wow.
This standard allows for high-performance, modular, and reusable designs that work right the first time. It really underpins the entire modern IP-centric SoC design methodology.
All right, so with that bigger picture in mind, how does AXI actually achieve all this behind the scenes? What are the core mechanics of how it moves data inside a chip?
Okay, so AXI uses what's called a channel-based architecture. Imagine 5 separate, dedicated express lanes for communication.
5 lanes, okay.
You've got the AEW, or address write channel. That's for sending write addresses and control signals. Then there's the W, or write data channel, for the actual data being written.
Makes sense.
For feedback on writes, there's the B, or write response channel. And then for reads, you have parallel channels. The AR, or address read channel, and the R, or read data channel for the data coming back.
So separate paths for reads and writes.
Exactly. And the genius of these independent channels is that reads and writes can happen simultaneously. That significantly boosts performance.
Concurrency.
Right. Now, all these channels use a remarkably robust valid-ready handshake. It's like a digital high five.
Yep.
The valid signal from the source says, hey, I have data ready, and the ready signal from the destination says, great, I'm ready to take it. A transfer, often called a beat, only happens when both signals are asserted, when they're both high.
Simple enough.
But here's the clever twist to prevent digital gridlock, or deadlock. The source must not wait for ready before asserting valid. It just puts the data out there and says it's valid.
Okay, so it doesn't wait for permission.
Correct. However, the destination is permitted to wait. It can hold off asserting ready if it's not quite ready yet. This asymmetry is crucial. It ensures robust flow control, accommodates variable delays between components, and allows for pipelining, keeping data flowing smoothly without imposing rigid, difficult timing constraints.
That's quite elegant, actually.
It is. AXI also operates on a straightforward master-slave model. A master initiates transactions. Think of it as the one asking for data or wanting to write something.
The initiator.
Exactly. And the slave is the one that responds, providing data or accepting it. Now, while AXI itself defines these point-to-point connections between one master and one slave,
Real chips have lots of things talking to each other.
Right. So in complex chips with many masters and slaves, you need an interconnect fabric. Things like the Xilinx AXI interconnect IP act like central traffic controllers, routing all those conversations between potentially many masters and many slaves.
Got it. The traffic cop.
Pretty much. And one of AXI's defining characteristics, especially for memory transfers, is burst transfers.
Okay, what are those?
Instead of sending one piece of data at a time for each address request, a single address request initiates multiple data items, or beats, in sequence.
More efficient?
Much more efficient. The master specifies the starting address, how many beats it wants, AXLIN, the size of each beat, AXIs, and the burst type, like fixed, same address, incrementing, next address, or wrapping, looping within a boundary.
How big can these bursts get?
Well, that's evolved. AXI3 could burst up to 16 beats, but AXI4 massively expanded that to 256 beats.
Wow, 256, that's a huge jump.
It is, especially important for transferring big chunks of data to and from things like DDR memory. And each individual beat, the data packet itself, can range from 1 byte up to 128 bytes wide.
Okay, what else makes AXI powerful?
Beyond those core ideas, AXI supports some advanced features. Things like multiple outstanding transactions, meaning a master can send several requests without waiting for each response first. Greatly improves parallelism.
To keep the pipeline full.
Exactly. And out-of-order completion, using ID tags. This allows faster transactions to finish first, even if they were requested later, which helps hide latency. It also handles unaligned data transfers using byte strobes, letting you access specific bytes within a larger data word. Very flexible. And for system designers trying to hit high clock speeds, it supports the easy insertion of pipeline registers, often called register slices, vital for meeting demanding timing requirements.
So it's really a combination of things working together.
Absolutely. The true brilliance of AXI's performance isn't in one single feature, but in how all these clever elements, the independent channels, the burst transfers, the out-of-order completion synergize. It's like a perfectly choreographed dance of data, masking latency, boosting efficiency, creating a highly concurrent and effective data flow model.
So we've clearly got the foundational concepts down now. Let's look at how this standard evolved. The AXI family isn't just one protocol, right? It's a group of specialized members. How did they each come to play their unique roles?
Yeah, that's a great point. When we zoom out and connect this to the bigger picture, the evolution of AXI really tells a story of addressing increasingly specialized design needs as chips became more complex and more powerful over time.
Okay, let's start at the beginning then. AXI3. This was the original part of AMBA3 back in, 2003. What were its key features?
Right. AXI3 was the pioneer. It established those 5 core channels and that crucial valid-ready handshake we just discussed.
The foundation.
The foundation. It supported burst lengths of up to 16 beats, which was pretty good for its time. AXI3 also featured something called write interleaving.
Write interleaving. What's that?
Imagine data from different write operations, maybe going to the same slave, could kind of merge onto the write data channel out of order. It used a special WID signal, a write ID, to keep track of which data beat belonged to which original write transaction so the slave could sort it out correctly.
Okay, a bit like shuffling cars onto a highway.
Sort of, yeah. It also allowed for locked transfers. This essentially gave a master exclusive access to a slave for a sequence of operations like putting a do not disturb sign on a specific register or memory region. And like its successors, it enabled multiple outstanding transactions, out-of-order completion with ID tags, and handled unaligned data transfers. Its flexible timing also allowed designers to easily insert those pipeline stages, which helped achieve high operating frequencies.
Where did AXI3 typically shine? What were its main applications?
AXI3 was primarily used in, high-frequency systems back then, connecting various IP blocks within SOSs and FPGAs, especially alongside high-speed processors like the ARM Cortex-A family. For instance, you might see it moving data from a digital signal processing or DSP block within an FPGA to an Ethernet interface, potentially routed via an ARM processor.
Yeah.
But while effective, early implementations with AXI3 could sometimes involve multiple bus bridges, which could add noticeable latency, especially if you were just reading single pieces of data occasionally. This revealed some limitations.
Right. So you start to think, well, why did it need to evolve? What were the shortcomings?
That 16-beat burst limit, while generally good, started becoming a bottleneck, especially for the higher bandwidth memory interfaces like modern DDR that were emerging.
Right. Needed more throughput.
Exactly. And features like Right interleaving and locked transfers, while they offered certain functionalities, could also introduce complexities in the interconnect arbitration logic and managing global ordering, especially when you had many different masters trying to talk at once. This created a need for, let's say, more predictability and better system-level performance.
So enter AXI4. This was the significant answer to those evolving needs, arriving in 2010 with AMBA4. This was really driven by the demand for enhanced performance in those increasingly complex multi-master saws, right?
Precisely. AXI4 brought several really key enhancements. First, the burst length was significantly extended. As we mentioned, instead of a maximum of 16 data beats, it could now transfer up to 256 beats in a single burst.
Game changer for memory.
Absolutely. A game changer for efficiently moving large blocks of data, especially to high-capacity memories like DDR. A fundamental change was the explicit removal of write interleaving.
Oh, they took it out.
They did. No more shuffling data from different write operations together on the W channel. This simplified the overall system design and made the WID signal redundant.
Yeah.
Similarly, lock transfers were no longer supported in the same way. AXI4 replaced this with a lighter weight mechanism for exclusive access that was less prone to causing system-wide stalls.
Interesting. What was added?
Two highly impactful additions were quality of service, QoS, and regions. QoS allows masters to signal the priority of their transactions. Think of it like a fast pass lane for critical data.
Right, letting important stuff cut in line.
Essentially, yes. It lets the interconnect prioritize bandwidth and reduce latency for urgent transfers. Regions, on the other hand, allow a single physical slave interface to manage up to 16 distinct logical memory areas. This simplifies how designers map memory within the chip. AXI4 also introduced optional user-defined signals, AXIs array, on each channel, giving designer space for custom sideband communication if needed. And it enforced stricter write response timing, ensuring all write data and the address are fully transferred before the completion response, pvalid, comes back.
More predictable.
More predictable. And finally, a subtle but powerful change. The AX catch signals were redefined. Instead of just indicating cacheable, they now signaled if a transaction was modifiable. This unlocks powerful system-level optimizations, like allowing the interconnect or memory controller to combine multiple small writes into one larger, more efficient transfer, or even prefetching data before it's explicitly requested.
So that feels like a real shift in focus.
It absolutely was. What's truly clever about these changes is that they reveal a strategic shift. AXI3 focused more on optimizing individual transactions, perhaps, but AXI4 pivoted to targeting system-wide throughput and manageability in these incredibly complex multi-master SOCs. Counterintuitively, removing some features, like write interleaving and locked transfers, actually simplified the overall arbitration process, improving predictability across the entire system.
So where do we typically see this full-fledged AXI4 in action, especially with its muscle for high bandwidth needs? Where is its sweet spot?
You'll primarily find AXI4 employed for high-performance memory map requirements, particularly when dealing with high-bandwidth DDR memories. For example, DMA controllers make extensive use of AXI4 master interfaces for those efficient burst reads and writes to DRAM, taking the load off the main processor. Many general-purpose peripherals that benefit from moving blocks of data, think sophisticated SD card controllers or high-speed Ethernet controllers, they often utilize AXI4. It's also very widely adopted in a Z-Link-based designs for tightly integrating custom IP logic in the FPGA fabric with their Zinc processing systems. And crucially, memory controllers themselves, particularly those interfacing with DDR memory, which has high initial access latency, benefit immensely from AXI4's longer burst capabilities and its support for multiple outstanding transactions. This helps mask that latency and dramatically improves overall memory throughput.
Now let's talk about AXI4 Lite, which actually arrived at the same time as AXI4 back in 2010. This is a streamlined subset of AXI4 designed for simplicity. You called AXI4 a heavy-duty truck. Maybe this is the compact car.
That's a perfect analogy. AXI4 Lite is indeed all about simplicity and efficiency for less demanding tasks. Its most fundamental simplification is that it has no burst capability whatsoever. Every single transaction is fixed at just one beat, one data transfer.
Just one and done.
Exactly. It also usually has a fixed data bus width, typically 32 or 64 bits, which means there's no need for an AXI signal to indicate the data width for each transfer.
Simpler signals.
Much simpler. It doesn't support exclusive accesses and doesn't use AXI transaction IDs either. It's too simple to need them. Its cache support is minimal, with the XCAS signals typically just hardwired to indicate non-modifiable and non-bufferable accesses.
Okay.
All these simplifications lead to significantly lower hardware complexity. It's much easier to design and implement, requiring fewer logic gates, fewer wires on the chip. But despite these reductions, it still uses the Core 5 AXI channels and that robust valid-ready handshake, so it maintains that fundamental AXI reliability.
So if it's so simplified, what are the typical use cases for AXI4 Lite? Where does this compact car really shine?
AXI4 Lite is perfect for simple, low-throughput memory-mapped communication. Its primary application is accessing and configuring control and status registers, CSRs, within IP blocks.
Ah, setting things up or checking status.
Exactly. Or for low-bandwidth sideband operations where high data throughput just isn't the priority. For instance, you might use an AXI4 Lite interface for configuring a DMA engine before it starts a large AXI4 transfer, or for accessing status registers like interrupt flags or error counters. It's also ideal for controlling custom IP block functions, maybe turning features on or off via registers. And in those Xilinx Zinc devices, it's very frequently used to connect the ARM processing system to the FPGA logic for simple control and status tasks. It's a really common setup.
So this really highlights a strategic design choice, doesn't it? Why would you deliberately opt for less capability?
It absolutely does. AXI4 Lite exemplifies the principle of using the right tool for the job. For these single-word, often infrequent accesses like reading a status register using the full AXI4 protocol would just add unnecessary logic, routing complexity, and power consumption.
Overkill.
Total overkill. AXI4 Lite perfectly balances the communication needs with resource optimization, making it incredibly efficient for its specific niche. It's about being smart with your resources.
Now, for what I think is the truly unique member of the family, AXI4 Stream. This one feels like it's playing a completely different game altogether. What makes it so distinct?
You're absolutely right to say that. Its most significant differentiator, the thing that sets it completely apart, is the complete removal of addresses.
No addresses at all.
None. Unlike the other AXI variants that are all about accessing specific memory locations, AXI4 Stream operates on a pure data-centric data flow paradigm. Addressing information is simply not present. This fundamental difference allows it to be highly optimized purely for continuous data movement.
Okay, so what are its key characteristics then?
Well, it features a unidirectional flow, strictly master to slave. It handles continuous data streams rather than traditional address-based bursts. Think of data moving in tackets or frames, potentially without an inherent length limit imposed by burst counters.
Like a fire hose of data.
Kind of, yeah. It also has incredibly flexible data width. The T-data bus width can be basically any integer number of bytes, 8 bits, 16, 32, 64, even up to 1024 bits wide or more. By eliminating addresses and all the related control signals, it has significantly reduced signal routing. Fewer wires, lower complexity, less resource consumption on the chip. It even supports shared wires, allowing you to multiplex multiple logical streams over a single physical connection using IDs. And crucially, for streaming applications like video or audio, there is no data reordering. Transfers are strictly in order. What goes in first comes out first.
Essential for that kind of data.
Absolutely. The minimum signals you need are just a clock, ACLK, TValid to say data is valid, TREADY to say you're ready, and TData, the data itself. Super simple core.
But there are optional signals too.
Yes, optional signals add powerful features. TLSC can indicate the end of a packet or frame. TD and TDST can provide stream or destination IDs for that multiplexing we talked about. TSDRB and TKeep act as byte qualifiers, indicating which bytes in TData are valid. And TOOSR provides a channel for application-specific sideband data, like maybe marking the start of a video frame.
What's really fascinating here is that removing addressing completely changes the game.
It really does. It shifts the paradigm from memory-mapped operations, which always have some address overhead, to continuous data flow. This drastically reduces overhead control signals, logic complexity, arbitration latency, allowing for maximum efficiency, and much higher throughput for unbounded streams of data. Signals like TLAST, TID, and TDS provide the necessary logical organization within the stream itself, entirely without relying on memory addresses. This specialization is precisely why AXI4 Stream achieves such substantial performance gains for streaming applications. It's incredibly efficient at what it does.
Give us some real-world examples. Where is this high-throughput specialist truly indispensable. Where do we see AXI4 Stream used most?
Okay, AXI4 Stream is ideal for any scenario involving high-speed continuous data. You'll find it extensively in digital signal processing DSP pipelines, where data flows directly from one processing block to the next, often without needing to hit main memory in between.
Makes sense.
It's absolutely critical in video processing, handling continuous streams of frames or pixels. Here, TLAST might signify the end of a video line or an entire frame, and 2 might mark the start of a frame.
Okay.
It provides direct, efficient interfaces for high-speed analog-to-digital converters, ADCs, and digital-to-analog converters, DACs, for real-time signal processing. Very common there. It's also very commonly used in direct memory access, DMA engines, specifically designed for streaming. You often see interfaces named things like SAXIS 2mm, which means Stream XIS, AXI Stream to memory mapped, or Maxis M2s, memory mapped to Stream XIS. These move large amounts of streaming data between processors or memory and FPGA logic efficiently.
Right, bridging the stream and memory worlds.
Exactly. You also see it powering network interfaces like Ethernet, handling the continuous flow of data packets, and in high-speed encryption units processing data streams. It's also vital for hardware-software co-design, enabling, for example, efficient data transmission of, say, waveform data from an ARM processor to FPGA logic for processing, without needing to buffer everything in main memory.
So connecting this back to the bigger picture.
AXI4 Stream's addressless, highly optimized data flow model directly meets the needs of continuous, high-speed, real-time data handling. This enables highly efficient hardware pipelines that would be incredibly difficult, maybe even impossible to achieve with the overhead of general-purpose memory-mapped interfaces. It's a perfect example of specialization driving peak performance for a specific class of problems.
We've walked through each member of the family now, seen their unique talents and specialties. Let's pull back a bit and really look at what they all have in common despite these differences, and where their defining divergences truly lie.
Yeah, and this brings us to a really compelling insight for anyone designing systems. How do you choose the right AXI variant for your specific need? Understanding these commonalities, and perhaps more importantly, the deliberate trade-offs, is absolutely key to making good engineering decisions.
Okay, so what's the common thread running through all of them?
Well, despite their distinct optimizations, all AXI family members share several foundational elements. They all originate from ARM's MEA specification, so they have a common pedigree.
Right.
They all employ a channel architecture in some form, whether it's the 5 distinct channels for memory-mapped variants or the single conceptual data channel for AXI4 Stream, enabling that concurrent data flow we talked about.
Okay.
A critical commonality across all of them is the universal valid-ready handshake for reliable data transfer, especially that crucial assert and wait rule, where the source must not wait for ready before asserting valid ready. It's like that digital handshake where the sender just puts the data out there reliably and the receiver is allowed to pause if needed.
That fundamental handshake.
That fundamental handshake,
Yeah.
yes. All operate on a master-slave model. They are fundamentally point-to-point specifications, which means that in real-world complex chips, those interconnect fabrics are always needed to manage the traffic between multiple masters and slaves. And they all share the common core design goals set out by ARM: high performance, scalability, flexibility, and low power. Another really significant point is that the AXI specification is a royalty-free standard that has contributed enormously to its widespread adoption and the huge ecosystem around it.
That's definitely key.
It is. The memory-mapped variants, AXI3, 4, and Lite, also commonly support unaligned data transfers using those byte strobes, WSTRB, letting you access specific byte lanes within a larger data word. Very useful flexibility. And finally, all AXI protocols are designed with easy insertion of pipeline stages or register slices in mind. That's vital for chip designers trying to achieve high operating frequencies and meet timing closure.
That consistent foundation really does simplify IP integration, doesn't it?
Yeah.
Even with the different functions. But let's really dig into those differences now, because that's where the design choices get interesting, right? That's where the specialization comes in.
Precisely. Let's try to distill it down. Maybe think of it as a clear comparison table in your mind.
Right.
First, the primary paradigm. AXI3, AXI4, and AXI4 Lite are all about memory map access, linking operations to specific memory addresses. AXI4 Stream, completely different, purely streaming, no addresses involved at all.
Memory versus stream. Got it.
For channels, the memory mapped variants use those 5 distinct channels, A, W, W, B, A, R, R. AXI4 Stream is conceptually just one main data channel, T-data plus controls.
5 versus 1 conceptual.
Right. Burst length is a major differentiator. AXI3 was limited to 116 beats. AXI4 massively increased that to 256 beats. AXI4 Lite is strictly fixed at 1 beat only. And AXI4 Stream has effectively unlimited length based on packets defined by TXI3.
Huge variation there.
Huge variation. Then remember, right, interleaving and locked transfers supported in AXI3, but importantly, they were removed from AXI4, AXI4 Lite, and AXI4 Stream to simplify system design and arbitration.
Okay, AXI3 only for those.
Correct. Advanced features like quality of service, QoS, and regions are found only in AXI4, offering transaction priority and segmented memory mapping.
AXI4 exclusives.
Exactly. Transaction IDs, AXI or TID, are supported in AXI3, AXI4, and AXI4 Stream for stream identification, but not in the simple AXI4 Lite.
Lite doesn't need them.
Right. Data bus width. Flexible for AXI3 and AXI4, AXI size. Fixed, typically 32 or 64-bit for AXI4 Lite. And almost any integer number of bytes for AXI4 Stream can data width to fit various data types perfectly.
Stream is super flexible.
Very data reordering. Allowed out-of-order completion for AXI3 and AXI4 to help hide latency. But AXI4 Stream is strictly in order, which is critical for continuous data streams. AXI4 Lite doesn't really apply here since it's only single transfers.
Order matters for Stream.
Absolutely. Their primary use cases align directly with these capabilities. High-performance SOS interconnect and DDR memory access for AXI3 and especially AXI4, simple control and status register access for AXI4 Lite, and ultra-high-speed continuous data streaming for AXI4 Stream.
Right, tool for the job.
Exactly. And finally, complexity and logic footprint. AXI4 is generally the highest in terms of complexity and resource usage. AXI3 is medium-high. And AXI4 Lite and AXI4 Stream are significantly lower, consuming fewer chip resources like logic gates and wires.
So let's really make those trade-offs concrete. How do these differences impact actual real-world design decisions? Can you give some examples?
Sure. First, let's compare AXI3 versus AXI4 again. AXI4's much longer bursts, up to 256 beats, directly address the needs of modern high-bandwidth memories like DDR4, DDR5, where you want to move huge chunks of data as efficiently as possible. AXI316 was often just too small.
Right. Bandwidth needs drove that change.
Definitely. And the removal of write interleaving and locked transfers in AXI4, while seemingly a reduction in features, actually streamlined the design of the interconnect arbitration logic, especially in complex multi-master systems. It made the entire system more predictable and easier to design and verify.
Simpler is sometimes better.
In this case, yes, for system predictability. And the addition of QoS in AXI4 allows for direct prioritization of critical traffic, maybe real-time video or urgent network packets, which is absolutely essential for guaranteeing performance in sensitive applications. This shift clearly indicates a move towards optimizing system-level throughput and manageability, rather than just optimizing individual point-to-point transactions like AXI3 might have focused on.
Okay, now how about AXI4 versus AXI4 Lite? The big versus the small.
Right. Full AXI4 is your powerful workhorse for memory-intensive, high-throughput operations like talking to main memory or high-speed peripherals. It's powerful, but it comes with higher complexity and uses more chip area and power. AXI4 Lite, however, is specifically designed and optimized for those simple, low-throughput control and status registers.
CSR.
The CSRs, exactly. It deliberately sacrifices performance features like burst capability and variable data width for a significantly smaller logic footprint and much easier integration. It's a classic engineering trade-off, fitting the interface precisely to the application. You balance peak performance needs for some tasks with optimal resource efficiency for the simpler ones. You wouldn't use a sledgehammer to hang a picture frame.
Good analogy. And finally, the fundamental split. Memory-mapped AXI34 Lite versus AXI4 Stream.
This is probably the biggest conceptual divide. Memory map protocols are address-based. They're incredibly versatile because you can, in theory, access any location in a memory map. But they inherently incur overhead generating addresses, decoding addresses in the interconnect, arbitration logic, the extra address signals themselves.
There's a cost to that flexibility.
There is. AXI4 Stream, on the other hand, is addressless. This drastically reduces the number of signals needed and the complexity of the control logic, making it extremely efficient for continuous unidirectional data streaming. It's specialized for data flow paradigms like video processing pipelines, DSP chains, network packet handling, where memory addresses are largely irrelevant for the core data path.
Streamlined for flow.
Perfectly put. It enables optimal performance and throughput in its niche, where address-based access would just add unnecessary baggage. The very existence of these distinct variants within the AXI family really highlights the critical need for specialized communication protocols to achieve the best possible performance and efficiency across the incredibly diverse requirements of modern chip design. There's no single one-size-fits-all solution.
This all sounds incredibly powerful and well thought out. But with great power, as they say, well, comes engineering challenges, right? It can't all be smooth sailing. What does it actually take to implement these protocols perfectly in complex, real-world designs?
That's the million-dollar question, isn't it? How do designers actually ensure these incredibly complex systems built using AXI work flawlessly? Because mistakes can be very costly.
I bet.
So as we discussed, AXI itself is fundamentally a point-to-point interface definition. But modern SoCs, modern chips, have dozens, sometimes hundreds, of masters and slaves, all needing to communicate. So you absolutely need an interconnect fabric for what we call NM, or multiple master to multiple slave topologies.
It's a central switchboard.
Exactly. Things like the Xilinx AXI Interconnect IP or their more advanced Smart Connect are crucial pieces of infrastructure. This fabric acts like a sophisticated highway system within the chip. It handles the arbitration, deciding which master gets access when multiple want the same slave. It handles address decoding to route transactions to the correct destination slave. It handles multiplexing multiple connections over shared resources. And it often needs to handle tricky things like clock domain crossings, CDCs, if different blocks run at different clock speeds.
Which they often do.
Which they often do, yes. And also data with conversions, if, say, a 64-bit master needs to talk to a 32-bit slave. For very large-scale sulpicius, these advanced interconnects are sometimes even referred to as network-on-chip or NO-C architectures. They become quite complex networks in their own right.
Okay, so you have that interconnect fabric in place. How do engineers then squeeze every last bit of performance out of AXI itself? What are the tricks of the trade for optimization?
Right, performance is key. For data transfer optimization, designers really focus on maximizing the use of those burst transfers, especially AXI4's long 256-beat bursts whenever possible. They also try to fully leverage out-of-order transactions using IDs to keep the communication pipelines full and high latency.
Yeah.
And they pay close attention to efficient data packing and unpacking to avoid wasting precious bandwidth on the wires.
Get the most out of every transfer.
Precisely. For latency reduction, the goal is often to get early responses back from slaves where possible, perhaps using speculative reads sometimes. Using AXI4's QoS effectively to prioritize critical traffic is huge for latency-sensitive applications. And strategic pipelining, carefully inserting those register slices within the AXI paths or the interconnect, is absolutely key to achieving higher clock frequencies without violating timing rules.
Balancing speed and reliability.
Exactly. And we can't forget power management. Modern chips are incredibly power sensitive, so designers employ techniques like clock gating, dynamically disabling the clocks to idle AXI blocks, or even power gating, cutting the power entirely to unused sections of the chip. And dynamic voltage and frequency scaling, or DVFS, which dynamically adjusts the operating voltage and clock speed based on the current workload, can save significant power during less intensive periods. AXI needs to work efficiently within these power management schemes.
Makes sense. So what are the biggest hurdles, or maybe the common gotchas, when bringing these complex AXI-based designs to life in actual silicon? Where do things tend to go wrong?
Well, a significant challenge stems from the sheer complexity and potential for divergent implementations. Even though the AXI specification is quite detailed, like many complex standards, it inevitably allows for some interpretation, some ambiguity. This means different IP vendors or even different teams within the same company might implement or interpret parts of the protocol subtly differently.
Compatibility issues.
Exactly. This can lead to tricky functional bugs when you try to connect these different pieces of IP together. And critically, these subtle mismatches or misunderstandings can sometimes open up security vulnerabilities, things like unintended data leakage between transactions, or even memory corruption possibilities. This requires extremely rigorous verification. The very flexibility that makes AXI powerful also, paradoxically, imposes a substantial burden on the verification effort needed to ensure correctness and security.
Okay, what else?
Deadlock prevention is another absolutely critical concern in any complex interconnect system. Remember that valid-ready handshake rule where the source must not wait for ready before asserting valid? That's specifically designed to prevent certain types of deadlocks at the interface level.
Right, the asymmetry.
Yes, but in the broader interconnect, especially with multiple outstanding transactions flying around, you need more. Interconnect fabrics often implement mechanisms like ensuring only a single slave per ID is targeted by outstanding transactions from a given master, or using specific arbitration policies to help prevent these digital traffic jams where everything grinds to a halt. In chip design, these traffic jams can be catastrophic, bricking the device.
Sounds like a nightmare.
It can be. Clock domain crossing CDC issues are also really prevalent and tricky. As we said, different modules often operate using independent clocks. When AXI signals have to cross between these different clock domains, which happens all the time in the interconnect, doing it improperly can lead to mid-S stability. That's where a signal gets stuck in an undefined, unstable state for a short time.
Not good.
Definitely not good. It can cause data incoherence, synchronization latency, and generally degraded AXI performance. Robust synchronization techniques using special circuits like multi-flop synchronizers are absolutely essential, but they do inherently add a little bit of latency to the path. It's a constant trade-off.
And verifying all this must be tough.
Extremely tough. That brings us to verification methodologies. Due to AXI's complexity and the potential for subtle bugs, rigorous verification is non-negotiable. Advanced simulation-based methods like the Universal Verification Methodology, or UVM, using System Verilog, are standard practice. These involve creating sophisticated test benches that generate constrained random stimulus and check protocol rules using assertions, System Verilog assertions, or SVAs. But even that might not be enough for critical interfaces. Designers also increasingly turn to formal verification techniques, using tools like symbiosis or commercial equivalence. Formal methods use mathematical techniques to actually prove that an implementation adheres to the protocol specification under all possible conditions, or to find counterexamples showing where it fails. This can catch those incredibly subtle corner case bugs that even millions of simulation cycles might miss. It's becoming essential for high-confidence AXI implementations.
So after this really deep dive, what does this all mean for you, the listener? What's the big takeaway?
Well, the AXI family is truly the de facto standard underpinning virtually all modern SoCs. You find it everywhere, from tiny microcontrollers to massive server chips. It's a remarkably sophisticated and adaptable approach to on-chip communication, with each variant, AXI3, AXI4, AXI4 Lite, AXI4 Stream, meticulously designed and optimized for specific performance goals and functional requirements. They collectively enable the complex, high-performance, and yet power-efficient chips that are absolutely fundamental to nearly all modern electronics you interact with daily.
It's truly amazing when you stop and think about it, how a set of communication rules, essentially an invisible digital language negotiated by engineers, can have such a profound impact on what our devices are capable of. It's the silent high-speed engine running behind so much of our modern technology.
Absolutely. And the continuous refinement and specialization within the AXI family and potentially future AMBA standards will undoubtedly remain critical for addressing the ever-evolving demands of future silicon designs. Think about AI accelerators, next-generation networking, maybe even interfaces for quantum computing down the line. Efficient communication will always be key. It's an ever-evolving field.
So a final thought for you to chew on. Next time you pick up your smartphone, stream a high-definition video instantly or interact with any smart device in your home or car, take a second to consider the invisible, unbelievably high-speed conversations happening inside those chips, orchestrated by complex protocols like AXI. It makes you wonder, what other invisible but absolutely crucial technologies do you think are powering our daily lives, often completely unnoticed yet utterly essential to how things work?